Hello there. I'm so glad you found your way here tonight. Wherever you are in the world right now, allow yourself to settle into this shared moment of stillness. Let the noise of the day fade away. Let your thoughts grow quiet, like distant galaxies drifting through the endless dark. Right now, as you listen to these words, the universe stretches out in every direction. Billions of light years of space filled with wonders we are only beginning to understand. And hidden within that vastness are mysteries so profound they challenge the very foundations of what we think we know. Tonight we journey into the unknown places of the cosmos. A realm where invisible forces shape the destiny of galaxies. Where space itself can bend and break. Where the boundary between existence and non-existence blurs into quantum shadows. We will explore dark matter that we cannot see but whose gravity sculpts the universe around us. We will discover dark energy that pushes space itself apart at ever-increasing speeds. We will peer into black holes where time slows and information may be lost forever. And we will wonder whether our universe is merely one among countless others in an infinite cosmic sea. All of it waiting to be shared in the stillness. Tonight, let's drift off together while exploring over 100 soothing facts about the greatest mysteries of the universe. There's no rush here. No test at the end. Just soft words and quiet wonders to carry you into rest. Welcome to Drowsy Discovery. I am glad you found your way here tonight. Perhaps you have had a long day. Perhaps you simply enjoy falling asleep to thoughts about the vast unknowns that surround us. Either way, this space is for you. There is something deeply calming about contemplating the mysteries of existence. Every question reveals new depths. Every answer leads to further wonder. The universe does not demand that we solve its riddles tonight. It simply invites us to marvel at how much remains to be discovered. You are connected to this story more than you might realize. The atoms in your body were forged in ancient stars. The forces that hold you together are the same forces that govern galaxies. The very fabric of space and time that cradles planets also cradles you in this quiet moment. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is relax. So settle in. Let your breathing slow. And let the weight of the day drift away like light fading into the cosmic void. The mysteries of the universe are patient beyond measure. Dark matter has been shaping galaxies for billions of years. Dark energy has been stretching space since before the first stars ignited. Black holes have been swallowing light and secrets since the universe was young. And yet, within all that ancient strangeness there is profound beauty. Patterns that repeat across scales. Symmetries that hint at deeper truths. Questions that remind us how much wonder still awaits. Tonight, we will wander through these magnificent unknowns. We will meet the forces that remain invisible and the structures that defy our understanding. But there is no hurry. The cosmos has been mysterious since the beginning of time. It can wait a little longer while you rest. Let us begin with the invisible substance that holds galaxies together. Most of the matter in the universe is completely invisible. When astronomers add up all the stars, planets, gas clouds, and dust in the cosmos, they account for only a small fraction of what must exist. Observations of gravity's effects reveal that something massive lurks unseen throughout the universe. This invisible substance does not emit light, absorb it, or reflect it, making direct detection extraordinarily difficult. Yet its gravitational influence is unmistakable. It sculpts the distribution of galaxies across cosmic scales and determines how fast celestial objects orbit one another. Without this hidden mass, the structures we see could not have formed. The visible universe of shining stars and glowing nebulae is merely the tip of a vast cosmic iceberg. Most of what exists lies in shadow, shaping reality from the darkness. Understanding this invisible component has become one of the central challenges of modern cosmology. Galaxies spin too fast to be held together by visible matter alone. Astronomers measuring the rotation speeds of spiral galaxies noticed a profound puzzle. Stars and gas at the edges of galaxies move just as fast as those near the center, defying expectations based on visible mass. If only luminous matter provided gravity, outer stars should orbit slowly and drift away over time. Instead, they cling to their galaxies as if held by an unseen hand. The flat rotation curves observed in galaxy after galaxy demand extra mass far beyond what telescopes can see. This discrepancy is consistent across galaxies of all sizes and types. The simplest explanation is that each galaxy is embedded in a massive halo of invisible matter, extending far beyond its visible disk. This realization transformed our understanding of galactic dynamics. Galaxies are not merely collections of stars, but complex systems dominated by hidden forces. An invisible force keeps stars from flying apart into the void. The gravity of visible matter alone cannot explain why stars remain bound within galaxies. At their observed speeds, stars should have escaped into intergalactic space long ago. Yet galaxies retain their shape over billions of years, spinning in graceful spirals or settled elliptical forms. Something unseen provides the additional gravitational glue required to maintain cosmic order. This invisible binding pervades not only galaxies, but also clusters of galaxies, where the same discrepancy appears on even larger scales. Hot gas within clusters moves too quickly to be held by visible mass. The temperatures of this gas, measured through X-ray observations, confirm the presence of enormous hidden mass. The pattern repeats everywhere astronomers look, from dwarf galaxies to the grandest superclusters. Nature has built a hidden framework that underpins the architecture of the cosmos. Without this unseen force, the universe as we know it would unravel into scattered, lonely drifts of stars. We call this hidden substance dark matter because it emits no light. The name dark matter reflects our ignorance as much as the substance's properties. It does not glow, shine, or scatter light in any detectable way. Telescopes tuned to radio waves, infrared, visible light, ultraviolet, X-rays, and gamma rays all fail to reveal it directly. Across the entire electromagnetic spectrum, from the longest radio waves to the most energetic gamma rays, dark matter remains utterly invisible to every instrument we have built. Only its gravitational effects betray its presence. Dark matter responds to gravity and exerts gravity in return, bending the paths of light and influencing the motion of stars. Beyond that, it appears to interact with ordinary matter and itself only weakly, if at all. This extreme elusiveness makes detection extraordinarily challenging, despite decades of dedicated experiments. It passes through planets and people as if they were phantoms. The term dark captures both the literal absence of emission and the conceptual mystery surrounding its nature. Identifying what dark matter truly is remains one of the most pressing questions in physics and astronomy. Dark matter outweighs ordinary matter by roughly 5 to 1. Measurements of the cosmic microwave background, galaxy clustering, and gravitational lensing all converge on a striking conclusion. The universe contains about 5 times more dark matter than ordinary atoms. Protons, neutrons, and electrons, the building blocks of everything we can see and touch, form only a minor component of cosmic mass. The rest is composed of this enigmatic dark substance, whose particles have yet to be identified. This dominance profoundly shapes the evolution of the universe. Dark matter's gravity seeded the formation of galaxies and large-scale structures. Ordinary matter fell into the gravitational wells dark matter created, eventually igniting into stars and planets. In a very real sense, we owe our existence to a substance we cannot see. The visible cosmos is a small ornament atop a vast hidden foundation. This realization has fundamentally changed how we think about the universe's composition and evolution. Fritz Zwicky first proposed dark matter in the 1930s. Swiss astronomer Fritz Zwicky studied the Coma cluster, a dense gathering of galaxies hundreds of millions of light-years away. He measured the velocities of individual galaxies within the cluster and found them moving far faster than expected. Applying the virial theorem, he calculated the mass needed to keep the cluster gravitationally bound. The result exceeded the visible mass by a factor of hundreds, a discrepancy so large it demanded explanation. Zwicky introduced the term Dunkelmaterie, German for dark matter, to describe this missing component. At the time, his bold claim was met with skepticism and largely ignored. Decades would pass before technology advanced enough to confirm his insight on galactic scales. Today, Zwicky is celebrated as a visionary who saw what others could not. His pioneering work laid the foundation for one of astronomy's greatest ongoing investigations. Vera Rubin confirmed its existence decades later through galaxy rotation curves. American astronomer Vera Rubin, working with Kent Ford, provided the definitive evidence that pushed dark matter into mainstream acceptance. In the 1970s, they carefully measured how fast stars orbit at various distances from the centers of spiral galaxies. Classical physics predicted that orbital speeds should decrease with distance, just as outer planets in our solar system move more slowly than inner ones. Instead, Rubin found that speeds remained roughly constant out to the visible edges and beyond. This flat rotation curve implied vast amounts of unseen mass enveloping each galaxy. The data was consistent across dozens of galaxies Rubin studied, forming an undeniable pattern. Her meticulous observations left little room for alternative explanations. Rubin's work transformed dark matter from a speculative idea into an observational necessity. She campaigned tirelessly for recognition of the problem's importance, inspiring generations of astronomers to search for answers. Every galaxy sits within an enormous halo of dark matter. Galaxies, as we observe them, are merely the luminous cores of much larger structures. Surrounding each galaxy is a spherical halo of dark matter, extending far beyond the visible disk. These halos can be 10 to 20 times larger in diameter than the starry portion we see in photographs. Within this invisible cocoon, stars orbit like fireflies suspended in an unseen mist. The dark halo provides the gravitational scaffolding that holds the galaxy together. Simulations show that halos formed first in the early universe, attracting ordinary matter that later condensed into stars. Without these dark matter cradles, galaxies would never have assembled. The halo also influences the motion of satellite galaxies and globular clusters orbiting the main galaxy. Every galaxy carries with it a vast, silent partner that shapes its destiny from the shadows. Dark matter bends light from distant galaxies through gravitational lensing. Einstein's general relativity predicts that mass warps the fabric of space-time, causing light to follow curved paths near massive objects. This prediction was first confirmed in 1919 during a solar eclipse, launching Einstein to international fame. Dark matter, though invisible, possesses mass, and therefore bends light, just as ordinary matter does. When light from a distant galaxy passes near a foreground cluster rich in dark matter, it is deflected, producing distorted arcs, multiple images, or magnified views. This phenomenon, called gravitational lensing, offers a powerful method to map invisible mass. The distorted images of background galaxies serve as natural telescopes, revealing the hidden architecture of the cosmos. By analyzing the shapes and positions of background galaxies, astronomers reconstruct the distribution of dark matter in the foreground. Lensing studies consistently reveal that clusters contain far more mass than their visible galaxies account for. The technique has become indispensable for understanding cosmic structure. Dark matter's gravitational signature is etched onto the sky in the bent light of distant worlds. The bullet cluster provides dramatic evidence for dark matter's existence. The bullet cluster is a famous collision between two galaxy clusters observed in the aftermath of a cosmic crash. As the clusters passed through each other, the hot gas that makes up most of their ordinary matter slowed due to friction and piled up in the center. Gravitational lensing maps, however, showed that most of the mass moved ahead, offset from the visible gas. This separation between visible matter and gravitational mass can only be explained if a massive collisionless component exists: dark matter. The dark halos passed through each other like ghosts, while the gas interacted and lagged behind. This observation is often cited as near proof of dark matter's reality. Alternative theories that modify gravity struggle to explain the bullet cluster's clear spatial separation. It remains one of the most compelling pieces of evidence in modern astrophysics. When galaxies collide, dark matter passes through like a ghost. Galactic collisions are spectacular events that unfold over hundreds of millions of years. Stars, though numerous, are so widely spaced that most pass without direct impact. Gas clouds, on the other hand, crash and heat up, emitting X-rays and generating shock waves. Dark matter behaves differently still. Because it interacts only through gravity, dark halos glide through one another almost entirely unimpeded. Simulations show that when two galaxies merge, their dark matter components overlap and then separate again if the collision is fast. This ghost-like behavior is exactly what observations of the bullet cluster and similar systems reveal. Multiple cluster collisions have now been studied, each confirming the same pattern of separation. Dark matter's indifference to ordinary atomic forces makes it uniquely suited to slip through cosmic traffic jams. Understanding how dark matter behaves in collisions helps constrain its possible properties and rules out certain particle candidates. Dark matter interacts only through gravity and possibly weak forces. Unlike ordinary matter, dark matter does not feel the electromagnetic force. It neither emits nor absorbs photons, rendering it invisible to all forms of light. It also appears unaffected by the strong nuclear force that binds protons and neutrons. The only interaction clearly demonstrated is gravity. Some theoretical candidates, such as certain weakly interacting massive particles, might also experience the weak nuclear force responsible for radioactive decay. If so, very rare collisions with ordinary nuclei could occur, providing a potential detection pathway. Experiments deep underground search for such faint signals, shielded from cosmic rays that would otherwise mask them. So far, no confirmed detection has been made. The extreme elusiveness of dark matter challenges the ingenuity of physicists and continues to drive ever more sensitive experiments. Trillions of dark matter particles may pass through your body each second. If dark matter is composed of particles roughly the mass of atoms or heavier, then their density in our galaxy implies a constant invisible rain. Every second, countless dark matter particles stream through the Earth, through walls, through every living thing. They interact so weakly that almost none ever collide with ordinary atoms. You would never notice their passage. This ghostly flux has been flowing since the formation of the Milky Way's dark halo billions of years ago. Detecting even a single collision requires enormous detectors made of extremely pure materials, operated far underground to reduce background noise. The sheer number of particles passing through us contrasts starkly with the rarity of any interaction. It is a humbling reminder of how much of the universe we are blind to. The invisible world permeates everything, yet science is only now learning to see its traces. Underground laboratories search for dark matter deep within mountains. To detect dark matter directly, scientists must shield their instruments from the constant bombardment of cosmic rays. Deep underground, hundreds or thousands of meters of rock absorb most incoming particles, creating a quiet environment for sensitive detectors. Laboratories beneath mountains in Italy, the United States, Canada, China, and other countries host experiments hunting for rare collisions. Detectors use materials like liquid xenon, germanium crystals, or superheated liquids to register the faint energy released when a dark matter particle nudges an atomic nucleus. Decades of effort have progressively ruled out many possible particle masses and interaction strengths. Each generation of experiments has pushed sensitivity to new limits, exploring regions of parameter space once thought promising. The null results, though frustrating, are valuable. They narrow the search and guide theoretical predictions. Each generation of experiments pushes sensitivity further, edging closer to either discovery or the elimination of once favored candidates. No dark matter particle has ever been directly detected. Despite enormous effort and investment, no experiment has yet unambiguously observed a dark matter particle interacting with ordinary matter. Claims of possible signals have not withstood independent verification. This absence of detection is itself informative, ruling out many theoretical models and particle properties. Some candidates once considered likely, such as certain versions of WIMPs, now face severe constraints. The search continues with larger, more sensitive detectors and novel technologies. Scientists also look for signals from dark matter annihilations or decays in space, seeking gamma rays or other particles produced when dark matter particles collide. Space telescopes have searched the galaxy's center and dwarf satellite galaxies for excess gamma radiation. So far, these indirect searches have also yielded no confirmed signal. The mystery endures, making dark matter one of the longest-running open questions in physics. Every negative result refines our understanding of what dark matter is not, gradually narrowing the possibilities. Patience and persistence remain essential as the hunt approaches ever more elusive quarry. WIMPs were once the leading candidate for dark matter particles. Weakly interacting massive particles, or emerged from particle physics theories as natural dark matter candidates with almost miraculous properties. They would have just the right characteristics, massive enough to provide gravitational effects, weakly interacting to avoid detection in light-based telescopes, and produced in the early universe in amounts consistent with observations. For decades, WIMPs dominated theoretical and experimental dark matter research, inspiring entire generations of experiments. The coincidence between their predicted abundance and the observed dark matter density seemed too elegant to be accidental, a phenomenon sometimes called the WIMP miracle. Supersymmetric extensions of the Standard Model predicted exactly such particles as natural byproducts. Yet despite intensive searches spanning multiple generations of increasingly sensitive detectors deep underground, no WIMPs have been found. Experiments have probed ever deeper into the parameter space where WIMPs should appear, forcing revisions of many theoretical models. While WIMPs are not ruled out entirely, their status as the frontrunner has significantly faded. The dark matter puzzle may require looking beyond the most popular ideas toward less conventional possibilities. Axions are another proposed dark matter particle still being sought. Axions are hypothetical particles proposed originally to solve a different puzzle in particle physics, related to the strong force and the absence of certain symmetry violations. They would be extraordinarily light, far less massive than electrons, with very feeble interactions that make them even harder to detect than WIMPs. If axions exist, they could have been produced abundantly in the early universe, forming a cold, diffuse background that behaves like dark matter. Detecting them requires specialized experiments using powerful magnetic fields to convert axions into detectable photons through a process called the Primakov effect. The ADMX experiment in the United States and similar facilities worldwide are actively searching for axion signals, gradually ruling out portions of the possible mass range. Axions remain one of the most compelling alternatives to WIMPs because they arise from well-motivated theoretical frameworks. If discovered, they would simultaneously solve two major mysteries in physics: the nature of dark matter and what is called the strong CP problem. The search for axions exemplifies how different areas of physics can unexpectedly connect and illuminate each other. Some scientists suggest dark matter could be primordial black holes. Primordial black holes are hypothetical objects that may have formed in the early universe, shortly after the Big Bang, during a brief window of extreme conditions. Unlike black holes born from collapsing stars millions or billions of years later, these would have arisen from extreme density fluctuations in the infant cosmos, when space was compressed to incredible densities. If they formed in the right mass range and abundance, they could account for some or all of the dark matter we infer from gravitational observations. Observations constrain their possible masses from both sides. Too small and they would have evaporated through Hawking radiation long ago. Too large, and they would produce detectable gravitational effects on stars, binaries, and the cosmic microwave background. A window of intermediate masses, roughly in the asteroid to small planet range, remains open and is under active investigation by multiple research groups. Gravitational wave observations of black hole mergers provide new constraints, as does microlensing of distant stars. The idea that dark matter might be macroscopic objects rather than exotic fundamental particles is appealing for its simplicity and testability. Yet proving or ruling out this hypothesis requires further observation and theoretical refinement. Without dark matter, galaxies and stars could never have formed. In the early universe, ordinary matter was too hot and uniform to collapse under its own gravity, because it was coupled to intense radiation. Radiation pressure kept atoms diffuse and scattered, preventing any clumping for hundreds of thousands of years. Dark matter, however, does not interact with light and felt no such pressure from the radiation bath. It began clumping together first, forming gravitational wells long before ordinary matter could join. Once the universe cooled sufficiently, about 380,000 years after the Big Bang, ordinary matter fell into these preformed dark matter structures. The earliest density fluctuations, tiny ripples in the primordial plasma, would never have grown into galaxies without dark matter's stabilizing influence through its gravity. Scientists have run computer simulations that confirm this dependence, showing that universes without dark matter remain featureless voids. Without this head start, the gentle density variations seen in the cosmic microwave background would never have grown into the galaxies we observe today. Dark matter acted as the invisible architect, shaping the blueprint upon which cosmic structure was built. The first structures to form in the universe were dark matter halos, with ordinary matter joining later to create the luminous galaxies we observe today. Stars, planets, and ultimately life owe their existence to this silent scaffolding. The structure of the cosmos is a monument to dark matter's patient, early influence. Dark matter served as the scaffolding for all cosmic structure. Computer simulations of the universe's evolution show that dark matter halos form hierarchically, with small clumps merging into larger ones over billions of years. Ordinary matter follows, drawn into the gravitational embrace of these invisible structures. The resulting pattern of galaxies, clusters, and filaments traces the underlying dark matter web. Without this scaffolding, the universe would be a featureless fog of diffuse gas. Dark matter's early clustering set the stage for every bright structure astronomers observe. The cosmic scaffolding is not static, it continues to grow as gravity draws structures ever closer. Observations of galaxy distributions across billions of light-years match predictions from simulations that include dark matter. This agreement is powerful confirmation that our understanding, though incomplete, captures essential truth. Dark matter wrote the skeleton upon which the luminous universe is draped. The cosmic web of galaxies traces the invisible dark matter skeleton. Surveys of millions of galaxies reveal a stunning pattern. Galaxies are not scattered randomly but arranged along vast filaments surrounding nearly empty voids. This cosmic web spans hundreds of millions of light-years, with dense clusters at the intersections of filaments. The structure matches simulations that begin with dark matter seeding early clumps. Ordinary matter fell into the gravitational channels carved by dark matter, lighting up the web with stars and galaxies. The voids, regions with little dark matter, remain nearly empty. Mapping the cosmic web provides a window into the initial conditions of the universe and the nature of dark matter itself. Different dark matter properties would produce subtly different web structures. Ongoing surveys aim to measure these differences with ever greater precision, hoping to reveal clues about the invisible substance that shapes our cosmos. Perhaps dark matter is not a particle but a modification of gravity. Not all scientists accept that dark matter is a new form of matter. Some propose instead that our understanding of gravity is incomplete at galactic scales. Modified Newtonian dynamics, or MOND, adjusts Newton's laws at very low accelerations to explain galaxy rotation curves without invoking invisible mass. MOND has had some successes in predicting galactic properties, but it struggles with larger structures like galaxy clusters and the cosmic microwave background. Relativistic extensions of MOND attempt to address these issues, but remain controversial. The bullet cluster's separation of mass from visible matter is particularly challenging for modified gravity theories. Most cosmologists favor dark matter, but the alternative view keeps researchers honest and spurs rigorous testing. Science thrives on debate, and the possibility that gravity itself holds surprises cannot be dismissed lightly. The mystery of dark matter may unlock entirely new physics. Dark matter sits outside the standard model of particle physics, which describes all known elementary particles and forces except gravity. Identifying dark matter would therefore reveal something fundamentally new about the universe. Candidates like WIMPs connect to supersymmetry and other extensions of the Standard Model, while axions link to quantum chromodynamics and the strong force. Sterile neutrinos, self-interacting dark matter, and primordial black holes offer alternative possibilities with distinct observational signatures. Each possibility opens different windows onto physics beyond our current understanding, potentially connecting to grand unified theories or quantum gravity. The search for dark matter is not merely a hunt for a missing piece, but an exploration of unknown territory that could transform multiple fields. Whichever answer nature provides will reshape our conception of reality and the laws governing it. The darkness hiding between the stars may illuminate the deepest layers of physical law. Something even stranger than dark matter is accelerating the cosmos. Dark matter, despite its mystery, at least behaves like familiar matter in one respect. It attracts through gravity. Yet, observations reveal another cosmic component with the opposite effect. Something is pushing the universe apart, causing its expansion to accelerate rather than slow down. This repulsive influence dominates the energy budget of the cosmos and operates on the largest scales. It does not clump like matter or dilute as space stretches. Its nature is even more elusive than dark matter's. Dubbed dark energy, it represents perhaps the deepest puzzle in modern physics. Understanding dark energy may require revising our notions of gravity, space, and even time itself. The cosmos is not merely expanding, but racing ever faster into an uncertain future, driven by forces we barely comprehend. The universe is not just expanding, but speeding up over time. For most of the 20th century, cosmologists assumed that the expansion of the universe was slowing down. Gravity from all the matter within should act as a brake, gradually decelerating the cosmic expansion. Observations in the late 1990s upended this expectation. Distant supernovae, used as standard candles to measure cosmic distances, appeared fainter than they should have if expansion were slowing. The universe is not merely coasting, it is accelerating. Space itself is stretching ever faster, carrying galaxies apart at increasing speeds. This discovery was so unexpected and so significant that it earned the Nobel Prize in Physics for the researchers involved. The accelerating universe demands an explanation, and that explanation has become one of science's greatest quests. In 1998, astronomers discovered cosmic acceleration. Two independent teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, announced nearly simultaneous results that revolutionized cosmology. By observing Type Ia supernovae in distant galaxies, they measured how fast space was expanding at various points in cosmic history. The data showed that the expansion rate was not decreasing as expected, but increasing. The discovery contradicted decades of theoretical assumptions and forced a fundamental rethinking of the universe's composition. Cosmologists were compelled to add a mysterious new component to their models, one that dominates the energy content of the cosmos. Confirmation followed quickly from other observations, including the cosmic microwave background and large-scale galaxy surveys. The discovery of cosmic acceleration stands as one of the most surprising and consequential findings in the history of astronomy. It opened a new era of research focused on understanding what drives the universe apart. Distant supernovae appeared dimmer than expected, revealing faster expansion. Type Ia supernovae occur when white dwarf stars accumulate enough mass to trigger thermonuclear explosions. Because these explosions release roughly the same amount of energy, their intrinsic brightness is known. By comparing this expected brightness to the observed brightness, astronomers can calculate how far away the supernova is. When researchers looked at supernovae billions of light-years distant, they found them dimmer than predicted for a universe expanding at a constant or slowing rate. The implication was stunning. Light had traveled farther than expected because space had stretched more than anticipated. This simple observation of dimmer than expected stellar explosions upended decades of cosmological assumptions. The only explanation consistent with all the data was that cosmic expansion is accelerating. These distant stellar explosions became beacons, illuminating a universe behaving in ways no one had foreseen. Supernovae continue to play a central role in refining our understanding of cosmic acceleration. This mysterious repulsive force is called dark energy. The term dark energy was coined to describe whatever is causing the universe to accelerate. Like dark matter, the name reflects our ignorance. We know something is there, but we do not know what it is. Dark energy acts as a kind of anti-gravity, pushing space apart rather than pulling matter together. It pervades all of space uniformly and does not clump into structures. Its density remains roughly constant even as the universe expands, unlike matter, which dilutes as space grows. This strange behavior is both a clue and a puzzle. Dark energy constitutes the largest component of the universe's energy content, yet its fundamental nature remains almost entirely unknown. Solving the mystery of dark energy is among the highest priorities in contemporary physics and astronomy. Dark energy makes up about 68% of the universe. Observations of the cosmic microwave background, galaxy clustering and supernova distances all converge on a consistent picture of the universe's composition. Roughly 68% is dark energy, about 27% is dark matter, and only about 5% is ordinary matter. The atoms that form stars, planets, and people are a small minority of what exists. All the ordinary matter we can detect through any means accounts for barely 5% of the cosmic energy budget. Dark energy dominates the cosmic energy budget, even though we have no direct detection of it and little understanding of its origin. This dominance has only become apparent in the last few billion years, as the universe expanded and matter diluted. The accelerating influence of dark energy now outpaces gravity's slowing effect, dictating the long-term fate of the cosmos. The proportions reveal a universe profoundly different from early 20th century expectations. The cosmological constant was Einstein's original idea for such energy. When Albert Einstein first applied his general theory of relativity to the universe, he found solutions predicting expansion or contraction. At the time, the prevailing view was that the universe was static. To achieve a stable cosmos, Einstein introduced a cosmological constant, a term representing energy inherent in empty space that could counteract gravity's pull. When Edwin Hubble discovered that the universe was indeed expanding, Einstein abandoned the constant, reportedly calling it his greatest blunder. Decades later, the discovery of cosmic acceleration resurrected the idea. A cosmological constant with just the right value could explain the observed acceleration. Whether dark energy truly is a cosmological constant or something more dynamic remains an open question. Einstein's old idea has found new life in the accelerating cosmos. Einstein once called the cosmological constant his greatest blunder. Einstein introduced the cosmological constant reluctantly, aiming to preserve a static universe that observations of the era seemed to support. When Hubble's observations revealed cosmic expansion, the need for a repulsive term vanished, and Einstein reportedly regretted ever adding it to his equations. The phrase "greatest blunder" was attributed to him by physicist George Gamow. Whether Einstein used those exact words is debated, but the sentiment reflects his feeling that he missed predicting the expanding universe. Ironically, the discovery of cosmic acceleration suggests that something very like the cosmological constant does exist, vindicating the term Einstein wished he had never written. His blunder may have been not the idea, but the premature abandonment of it. History has treated Einstein's addition with unexpected kindness. Quantum field theory predicts vacuum energy, but gets the value wildly wrong. In quantum mechanics, empty space is not truly empty. Virtual particles continually pop in and out of existence, contributing energy to the vacuum. Quantum field theory allows physicists to estimate this vacuum energy, but the result is absurdly large, many orders of magnitude greater than the observed dark energy density. If the vacuum had the energy predicted, the universe would have expanded so violently that no galaxies or stars could ever form. This discrepancy, sometimes called the cosmological constant problem, is one of the worst theoretical predictions in the history of physics. The gap between theory and observation is so staggering that it suggests something fundamental is missing from our understanding. No accepted mechanism explains why the observed vacuum energy is so small yet not zero. Resolving this puzzle may require entirely new concepts that lie beyond our current understanding of quantum fields and gravity. The discrepancy is the worst theoretical prediction in all of physics. The mismatch between quantum field theory's estimate of vacuum energy and the observed value spans roughly 120 orders of magnitude. No other theoretical prediction in science has been so spectacularly wrong. Physicists have proposed various mechanisms to cancel or suppress the vacuum energy, but none has succeeded convincingly. Supersymmetry offers partial cancellations, but not nearly enough, and requires unobserved particles that experiments have so far failed to detect. Some invoke anthropic reasoning, arguing that only universes with small vacuum energy can support observers. Others suspect that our understanding of quantum gravity is fundamentally incomplete. The cosmological constant problem sits at the intersection of quantum mechanics, gravity, and cosmology, making it a uniquely difficult challenge. Solving it would likely require a profound conceptual breakthrough that reformulates our understanding of space, energy, and the vacuum itself. Dark energy does not dilute as the universe expands. Ordinary matter and dark matter become less dense as the universe grows. Like marbles spreading across an inflating balloon, the same amount of mass occupies ever more space. Dark energy behaves differently. Its density remains approximately constant, regardless of how much space stretches. This peculiar property is characteristic of the cosmological constant, where energy is intrinsic to space itself. As new volume is created, new vacuum energy appears, keeping the density steady. The constancy of dark energy density explains why its influence has grown dominant. Early in the universe, matter was densely packed and dominated cosmic dynamics. As expansion diluted matter, dark energy's unchanging contribution eventually took precedence. This transition marks the point at which the universe's fate was sealed toward eternal acceleration. Its influence has grown stronger as matter becomes more spread out. Billions of years ago, the universe was smaller and matter more concentrated. Gravity from this dense matter slowed the expansion, even if it could not halt it. As the universe expanded, matter diluted while dark energy remained constant. The balance tipped about 5 billion years ago, when dark energy's repulsive pressure began to dominate. Since then, the acceleration has increased, pushing galaxies apart ever faster. The universe is now firmly in the grip of dark energy, with its influence growing with each passing eon. Future observers, if any exist, will see an ever emptier sky as distant galaxies recede beyond the horizon. Dark energy's growing dominance is reshaping the structure and destiny of the cosmos in ways that were unimaginable just a few decades ago. About 5 billion years ago, dark energy became the dominant force. The transition from a matter-dominated to a dark energy-dominated universe happened roughly 5 billion years in the past, around the time our solar system was forming. Before that epoch, gravity from matter governed cosmic evolution, slowing the expansion established by the Big Bang. After the transition, dark energy's repulsive effect overtook gravity. The cosmic deceleration that had persisted for billions of years reversed into acceleration. The universe entered a new phase of expansion that continues to accelerate today. This crossover is not arbitrary. It depends on the precise densities of matter and dark energy, values that cosmologists have measured with remarkable precision. Understanding why these densities are so close in magnitude today, a puzzle called the coincidence problem, remains an active area of research. We happen to live near this pivotal era, a fact that may or may not be mere coincidence. Galaxies are now drifting apart faster than ever before. Cosmic acceleration means that the space between galaxy clusters is stretching at an ever-increasing rate. Galaxies are not moving through space away from one another. Rather, the space itself is expanding, carrying galaxies along for the ride. The farther away a galaxy is, the faster it appears to recede, a relationship known as Hubble's law. With acceleration added, this recession speed increases over time. Galaxies at the edge of the observable universe are already receding faster than the speed of light relative to us. Light they emit today will never reach us, forever red-shifted beyond detection. This does not violate relativity, because nothing is moving through space faster than light. Space itself is doing the stretching. The accelerating drift ensures that distant realms will become ever more isolated. Cosmic neighborhoods that once might have connected will drift forever apart. Distant galaxies will eventually fade beyond our observable horizon. The observable universe has a boundary set by how far light has been able to travel since the Big Bang. As the universe accelerates, this horizon does not simply grow. Instead, distant objects recede faster than new light can bridge the gap. Galaxies currently at the edge will eventually cross the cosmic horizon and vanish from view entirely. Their light, stretched to infinite wavelengths, will no longer reach us. Over trillions of years, the night sky will empty as galaxies disappear one by one. Eventually, only our local group of galaxies, bound by gravity, will remain within reach. The rest of the cosmos will be effectively beyond our cosmic event horizon. Future civilizations, if any exist that far in the future, may have no evidence that other galaxies ever existed. The universe may end in a cold, dark emptiness called the Big Freeze. If dark energy remains constant or grows slowly, the universe will continue expanding forever. Galaxies will drift apart, stars will exhaust their fuel, and new star formation will cease. Over immense timescales, even stellar remnants will fade, leaving behind cold white dwarfs, neutron stars, and black holes. Black holes themselves will eventually evaporate through Hawking radiation, leaving only the faintest particles drifting through endless dark. This fate, known as the Big Freeze or heat death, represents maximum entropy, a universe in thermal equilibrium with no energy gradients left to drive change. It is a serene but desolate vision, where nothing of significance can ever happen again. This is the ultimate thermodynamic equilibrium, a state of maximum entropy from which no escape is possible. The cosmos would become an eternal, motionless stillness, far removed from the bustling universe we inhabit today. If dark energy strengthens over time, a big rip could tear atoms apart. Some models of dark energy propose that its repulsive effect intensifies as the universe ages. In the most extreme scenarios, known as the Big Rip, dark energy would eventually overcome not just gravity but all binding forces. First, clusters of galaxies would unbind, then individual galaxies, then solar systems. Eventually, atoms themselves would be torn asunder, and space-time would rip apart in a catastrophic finale. The Big Rip is a speculative endpoint not supported by current observations, which favor a constant dark energy density. Yet it remains a possibility that cannot be ruled out. Understanding whether dark energy is truly constant or evolving is a key goal of ongoing and future surveys. The nature of dark energy may determine not just how the universe expands, but whether it survives at all. Understanding dark energy may reveal the ultimate fate of everything. The destiny of the cosmos hinges on the nature of dark energy. If it remains constant, the universe faces a big freeze. If it grows stronger, a big rip may await. Some models propose that dark energy could decay away, potentially leading to collapse in a big crunch. Other exotic possibilities include cyclic universes and phase transitions that reset the cosmos. Currently, observations slightly favor a cosmological constant, but uncertainties remain. Precision measurements of the expansion history and the growth of structure are the tools astronomers use to discriminate among models. Multiple independent methods now probe dark energy's equation of state with increasing accuracy. Every new supernova survey, every galaxy map, and every cosmic microwave background analysis brings us closer to understanding the distant future. Dark energy holds the script for the final act of cosmic history. Some propose that dark energy is a dynamic field called quintessence. Not all cosmologists believe dark energy is a simple cosmological constant. An alternative is quintessence, a dynamic field that evolves over time through the universe. Unlike a constant, a quintessence field could change its density and pressure as the cosmos ages. This would produce subtle variations in the expansion history that telescopes might detect. Different forms of quintessence are tied to different physical models, some arising from particle physics, others from modifications of gravity. The field might couple to dark matter, or even to ordinary matter in subtle ways. Distinguishing quintessence from a cosmological constant requires extremely precise measurements across billions of years of cosmic history. Ongoing and future surveys are designed with this goal in mind. If quintessence is discovered, it would open new frontiers in fundamental physics, linking cosmology to quantum fields in unexplored ways. New telescopes are mapping the expansion history with unprecedented precision. Space missions like Euclid and the Nancy Grace Roman Space Telescope are designed to measure cosmic expansion and the growth of structure with extraordinary accuracy. Ground-based surveys continue to catalogue millions of galaxies, supernovae, and gravitational lensing signals. These datasets allow cosmologists to reconstruct how fast the universe expanded at different epochs. By comparing the expansion history to theoretical models, scientists can test whether dark energy is constant or evolving. The precision achieved in recent years has already tightened constraints on dark energy properties. Future observations will push sensitivity to the point where tiny deviations from a cosmological constant could be detected. Each new telescope adds pieces to the puzzle, slowly assembling a portrait of the force shaping the cosmos on the grandest scales. Black holes are regions where gravity becomes infinitely strong. A black hole forms when mass is compressed into a volume so small that the escape velocity exceeds the speed of light. Nothing, not even light itself, can break free from within the event horizon. Classical general relativity predicts that at the center lies a singularity, a point of infinite density and curvature. Our physical laws break down there, unable to describe what happens when space-time is curved so extremely. Black holes warp space and time around them in ways that defy ordinary intuition. Time slows dramatically near the horizon as seen by distant observers. Yet to a falling observer, the crossing may seem unremarkable until tidal forces become overwhelming. The difference between these two perspectives illustrates how profoundly gravity distorts space and time. Black holes are laboratories of extreme physics, testing the limits of our understanding of gravity, matter, and the nature of reality. They form when massive stars collapse under their own weight. Stars balance gravity against the pressure of nuclear fusion. When a massive star exhausts its fuel, the core collapses in a fraction of a second. If the core's remnant exceeds a critical mass, no known force can halt the inward fall. The matter crushes down to a singularity, leaving behind an event horizon. The outer layers may explode outward in a supernova, briefly outshining entire galaxies, while the core becomes a stellar mass black hole. Some black holes grow much larger by accreting gas and merging with one another over cosmic time, reaching millions or billions of solar masses. These supermassive black holes reside at the centers of most galaxies, including our Milky Way. The birth and growth of black holes are integral to the life cycles of stars and galaxies. At the center lies a singularity where known physics breaks down. General relativity predicts that all the mass of a black hole collapses to a single point of infinite density, the singularity. At this point, space-time curvature becomes infinite, and the equations of classical physics produce nonsensical results. Quantum mechanics, too, has no tested theory that applies under such extreme conditions. Resolving the singularity is one of the holy grails of theoretical physics, potentially requiring a full theory of quantum gravity. Some proposals suggest that quantum effects halt the collapse before true infinity is reached, replacing the singularity with a very dense but finite core. Others invoke exotic structures like wormholes or phase transitions to new physics. Until a working quantum gravity theory emerges, the nature of the singularity remains profoundly mysterious. The event horizon marks the boundary of no return. An event horizon is not a physical surface, but a mathematical boundary defined by the point at which escape velocity equals the speed of light. You could pass through without noticing anything special at the moment of crossing. Cross it, and nothing can return to the outside universe. For an observer falling in, the crossing may not feel special. Local physics remains normal until tidal forces grow significant. The infalling observer would continue past the horizon, unaware they had crossed the point of no return. For a distant observer, however, the falling object appears to slow, redden, and freeze at the horizon, its image fading over time. Information about what lies inside is causally disconnected from the external universe. The horizon is a one-way membrane, letting matter and light in, but nothing out. Its existence is a prediction of general relativity, now confirmed indirectly through observations of accretion disks and gravitational waves. Nothing that crosses the event horizon can ever escape. Once inside the event horizon, all paths through space-time lead inexorably toward the singularity. Not even light, the fastest thing in the universe, can find a trajectory outward. This causal isolation is what makes black holes so mysterious. Whatever falls in is cut off from the rest of the cosmos, hidden behind an impenetrable boundary. Even information about the infalling matter seems trapped, leading to profound paradoxes when combined with quantum mechanics. Hawking radiation, the faint glow predicted to emanate from black holes, offers a possible loophole, but the mechanism by which information might escape remains hotly debated. For now, the event horizon stands as a cosmic prison, sealing away matter and energy in a vault that gravity alone can guard. Light itself falls inward once it passes that invisible threshold. Within the event horizon, space-time is so severely warped that every possible direction, even outward, leads toward the singularity. Light, which always travels along the quickest paths, finds no route that leads away from the center. Photons emitted inside the horizon spiral helplessly inward. From the outside, the black hole appears utterly dark because no light can escape to reach our eyes. The only glow visible from afar comes from matter falling toward the horizon, heated to extreme temperatures before crossing. Once that light source vanishes behind the boundary, silence reigns. The darkness of a black hole is not merely the absence of illumination, it is the absence of any signal that could ever reach us. It represents a fundamental limit on what we can know about the universe's hidden regions. Light, our swiftest messenger, cannot outrun the grip of such immense gravity. Time slows dramatically near a black hole due to extreme gravity. General relativity predicts that gravity affects the passage of time. Near a black hole, where gravity is immense, clocks tick more slowly relative to those far away. An astronaut hovering near the event horizon would experience time normally from their own perspective, yet distant observers would see them moving in slow motion. As the astronaut approached the horizon, their image would redden and freeze, never quite appearing to cross. This effect, called gravitational time dilation, has been confirmed at smaller scales near Earth and the Sun. Near black holes it becomes extreme, with time nearly halting at the horizon as seen from afar. The interplay of space and time near a black hole reveals the deep interconnection of gravity and the fabric of reality itself. A black hole is defined only by its mass, spin, and charge. Despite their exotic nature, black holes are remarkably simple objects according to classical general relativity. The no-hair theorem states that a stationary black hole is completely characterized by just three numbers: its mass, its angular momentum or spin, and its electric charge. All other information about the material that formed the black hole is hidden behind the event horizon. Two black holes with identical mass, spin, and charge are indistinguishable, regardless of how they formed. This simplicity is both elegant and troubling. It suggests that black holes erase the details of their origin. Connecting this classical description to quantum mechanics, which insists that information cannot be destroyed, lies at the heart of the black hole information paradox. Stephen Hawking predicted that black holes emit faint radiation. In 1974, Stephen Hawking made a remarkable theoretical discovery. By applying quantum field theory near the event horizon, he showed that black holes are not perfectly black. They emit a faint glow now called Hawking radiation. This radiation arises from quantum effects at the horizon, where virtual particle pairs can be separated before annihilating. One particle falls in while the other escapes, carrying away energy. The escaping radiation corresponds to a thermal spectrum, as if the black hole had a temperature. Stellar mass black holes are incredibly cold, far colder than the cosmic microwave background that bathes the universe. The larger the black hole, the cooler this temperature, and the fainter the radiation. Hawking's prediction was revolutionary, linking gravity, quantum mechanics, and thermodynamics in ways never before imagined. Although too faint to detect from astrophysical black holes, the concept has reshaped theoretical physics. Hawking radiation arises from quantum effects near the event horizon. In the quantum vacuum, pairs of virtual particles constantly appear and vanish. Near a black hole's event horizon, one member of a pair can be captured by the black hole, while the other escapes to infinity. The escaping particle carries positive energy, so from the outside it appears as real radiation. To conserve energy, the black hole must lose a corresponding amount, effectively shrinking over time. This process is extraordinarily slow for stellar mass black holes, with evaporation timescales far exceeding the current age of the universe. For very small black holes, however, Hawking radiation would be intense enough to cause rapid evaporation. The mechanism remains theoretical. No laboratory or telescope has observed Hawking radiation directly. Yet its prediction has profound implications for our understanding of space-time, entropy, and information. Over immense timescales, black holes slowly evaporate away. Hawking radiation carries energy away from a black hole, causing it to shrink. As the black hole loses mass, it radiates faster, accelerating its decline. Over almost unimaginable timescales, eventually the black hole vanishes entirely in a final burst of high-energy radiation. For a stellar mass black hole, this process would take roughly 10 to the 67 years, vastly longer than the universe's current age of about 14 billion years. Supermassive black holes would endure even longer. In the far distant future, long after stars have ceased to form and the cosmos has grown cold, black hole evaporation may be the dominant transformation left. When the last black holes evaporate, only the faintest particles and radiation will remain, marking a universe in its final stage of heat death. When a black hole vanishes, what happens to everything it consumed? As a black hole evaporates through Hawking radiation, all the matter and energy that ever fell in disappears along with it. The radiation emitted appears to be thermal, encoding no information about the original objects. If the black hole evaporates completely, where does the information go? Quantum mechanics insists that information is never truly lost. It can be scrambled but not erased. This clash between black hole physics and quantum theory is known as the information paradox. Resolving it may require radical new ideas about the nature of space-time, quantum gravity, or even the meaning of information itself. The paradox has fueled decades of theoretical work and remains one of the deepest open questions in physics. Whatever the answer, it promises to reshape our understanding of reality. This is the black hole information paradox. The black hole information paradox crystallizes a fundamental conflict between two pillars of physics. General relativity describes how matter falls behind the event horizon and is causally disconnected from the outside. Quantum mechanics demands that the evolution of physical systems be unitary, meaning information is conserved. If Hawking radiation carries no imprint of the infalling matter, information seems lost when the black hole evaporates, violating quantum principles. Physicists have proposed various resolutions, from remnants that store information to modifications of quantum mechanics itself. String theory and the holographic principle have offered intriguing clues, suggesting that information may be encoded on the boundary of space. Yet no consensus has emerged. The paradox continues to drive theoretical advances, pushing us toward a deeper understanding of how gravity and quantum mechanics must ultimately unite. quantum mechanics says information can never truly be destroyed. In quantum theory, the time evolution of a system is described by a unitary operator, a mathematical structure that preserves distinction between states. This means that, in principle, knowing the present state allows one to reconstruct the past or predict the future exactly. Information about any initial configuration persists, even if scrambled beyond practical recovery. Burning a book destroys it visibly, but the information still exists in the ashes, smoke, and radiation, at least in principle. Black holes challenge this idea because Hawking radiation appears thermal, carrying no memory of what fell in. If information truly vanishes when a black hole evaporates, quantum mechanics must be revised. Most physicists are reluctant to abandon unitarity, preferring to believe that information escapes through some subtle mechanism yet to be fully understood. Hawking radiation appears to carry no imprint of the swallowed matter. The thermal nature of Hawking radiation poses the central puzzle. Thermal radiation is characterized solely by temperature, with no structure that could encode detailed information about its source. If the radiation from an evaporating black hole truly contains nothing more than a temperature, then the vast reservoir of information that fell in over the black hole's lifetime would be erased. This violates the expectation that quantum evolution preserves information. Researchers have proposed that subtle correlations in the radiation, imperceptible at first glance, might encode the missing data. Demonstrating this rigorously requires a full theory of quantum gravity, which remains elusive. The apparent featurelessness of Hawking radiation is both a theoretical prediction and the crux of a paradox that continues to puzzle the brightest minds. Resolving the paradox may require a revolution in fundamental physics. The black hole information paradox sits at the intersection of gravity and quantum mechanics, two theories that have never been fully unified. Attempts to solve the paradox have led to radical proposals that space-time itself emerges from quantum entanglement, that event horizons are not as smooth as expected, or that the interior of a black hole is somehow encoded on its surface. String theory, loop quantum gravity, and holography have all contributed insights, yet a definitive answer remains out of reach. Solving the paradox would likely require conceptual breakthroughs comparable to those that gave us relativity and quantum mechanics in the first place. The resolution, when it comes, may reshape our understanding not just of black holes but of reality itself. Black hole entropy is proportional to the area of the event horizon. In the early 1970s, Jacob Bekenstein and Stephen Hawking discovered a remarkable relationship. The entropy of a black hole, a measure of its hidden internal states, is proportional not to its volume, but to the surface area of its event horizon. This is measured in Planck units, the fundamental scale where quantum effects and gravity are equally important. At this scale, our ordinary notions of space, time, and information must be radically revised. For ordinary objects, entropy scales with volume, so the black hole result is deeply surprising. It suggests that the maximum amount of information a region can hold is limited by its boundary, not its interior. This insight laid the groundwork for the holographic principle, one of the most important ideas in theoretical physics. Understanding why entropy lives on the horizon may reveal the quantum structure of spacetime. This suggests information is encoded on the boundary, not the interior. The Bekenstein-Hawking formula links black hole entropy to the area of the event horizon, rather than to its volume. This counterintuitive result hints that all the information about what fell into a black hole is somehow recorded on its two-dimensional surface. If true, The three-dimensional interior may be a kind of projection of data stored on the boundary. The idea generalizes beyond black holes to the holographic principle, which proposes that any region of space can be fully described by information on its enclosing surface. Physicists have found mathematical support for this in string theory, where a precise correspondence exists between gravitational theories and lower-dimensional quantum theories. The implication is profound. Space itself may emerge from an underlying quantum description that lives on a boundary. This conceptual shift is reshaping our understanding of gravity and the fabric of the cosmos. The holographic principle proposes that reality is a cosmic hologram. According to the holographic principle, all the information contained within a volume of space can be represented by data on the boundary of that region. Just as a two-dimensional hologram can encode a three-dimensional image, the universe itself may be an elaborate projection from a lower-dimensional surface. This radical idea emerged from studies of black hole thermodynamics and was given precise mathematical form by Juan Maldacena in 1997 through a proposal known as ADS-CFT. In this framework, a gravitational theory in a higher dimensional space is equivalent to a quantum field theory on its boundary. The equivalence has passed numerous theoretical tests, suggesting it captures something deep about nature. If holography applies to our universe, then space, time, and gravity may all emerge from a fundamentally different holographic description. Wormholes and quantum entanglement may be secretly connected. In a striking conjecture known as ER equals EPR, physicists Leonard Susskind and Juan Maldacena proposed that wormholes and quantum entanglement are two manifestations of the same underlying phenomenon. Einstein and Rosen studied wormholes in 1935, the same year Einstein, Podolsky, and Rosen explored entanglement. The conjecture suggests that pairs of entangled black holes are connected by a non-traversable wormhole through spacetime. If true, the fabric of space itself may be woven from quantum correlations. This idea has profound implications for the black hole information paradox, suggesting that information might be transferred through subtle spacetime bridges. The connection between geometry and quantum information has become a central theme in theoretical physics. Although still speculative, ER equals EPR points toward a deep unity between gravity and quantum mechanics. Black holes push the boundaries between quantum mechanics and gravity. Near a black hole, both quantum effects and strong gravitational fields become important, creating a natural laboratory for testing the interface between these two pillars of physics. Hawking radiation, a quantum phenomenon, arises precisely because of the extreme gravity at the event horizon. The information paradox forces us to confront how quantum rules apply when space-time geometry itself becomes the subject. Black holes also provide the best evidence for the holographic principle, which links gravity to quantum information. Observations of black hole mergers through gravitational waves have begun to probe the strong field regime of general relativity. Future measurements may reveal subtle quantum corrections to classical predictions. Black holes thus serve as the crucible where our deepest theories are tested and refined toward a unified understanding. Quantum mechanics and general relativity are incompatible at extreme scales. General relativity describes gravity as a smooth curvature of spacetime, while quantum mechanics describes matter and energy as discrete quanta subject to uncertainty. When physicists try to combine these frameworks mathematically, the equations produce infinities that cannot be removed by standard techniques. This clash is most severe at the Planck scale, where distances are about 10 to the minus 35 meters and times about 10 to the minus 43 seconds. At such extreme scales, quantum fluctuations of spacetime become significant, and the smooth geometry of relativity breaks down. Neither theory alone suffices to describe black hole singularities or the Big Bang. The incompatibility is not merely a technical issue, it signals that our fundamental understanding of nature remains incomplete. Resolving this conflict is one of the greatest challenges in physics. Both theories work perfectly in their own domains but clash when combined. General relativity has been confirmed by observations ranging from the bending of starlight to gravitational waves from merging black holes. Quantum mechanics underlies all of modern chemistry, electronics, and particle physics. In everyday circumstances and most astrophysical settings, the two theories can be applied separately without conflict. Problems arise only when both gravity and quantum effects are strong simultaneously, such as near singularities or at cosmological beginnings. In these regimes, there is no tested framework to combine them. Physicists have developed partial approaches, but a complete, consistent theory of quantum gravity remains elusive. The success of each theory in its own realm makes the clash all the more puzzling, suggesting that a deeper unification must exist waiting to be discovered. Finding a theory of quantum gravity is a holy grail of physics. A complete theory of quantum gravity would unite general relativity and quantum mechanics into a single consistent framework. It would explain what happens at the centers of black holes, describe the very first instance of the Big Bang, and potentially reveal new physics at tiny scales. Candidates include string theory, which replaces particles with vibrating strings, and loop quantum gravity, which quantizes spacetime itself. Both have achieved partial successes and face significant challenges. Other approaches explore emergent gravity, causal sets, and asymptotic safety. Despite decades of effort, no theory has yet produced definitive testable predictions that experiments can verify. The quest continues to inspire some of the most creative and rigorous work in theoretical physics. Young researchers around the world are drawn to this ultimate challenge, seeking to unify our understanding of nature at its deepest level. Whoever solves this puzzle will reshape our understanding of the cosmos. String theory proposes that all particles are vibrating strings. In string theory, the fundamental building blocks of the universe are not point-like particles but tiny one-dimensional objects called strings. Different vibrational patterns correspond to different particles. One mode might be an electron, another a photon, yet another a graviton. This elegant idea naturally includes gravity and offers hope for unifying all forces. For the mathematics to be consistent, string theory requires extra spatial dimensions beyond the 3 we perceive, typically 6 or 7 additional dimensions, curled up at scales too small to observe. The theory has produced profound insights into black holes, holography, and quantum geometry. Critics note that it has not yet made testable predictions accessible to experiment. Nonetheless, string theory remains one of the most intensively studied approaches to quantum gravity. String theory requires extra dimensions beyond the 4 we experience. For the equations of string theory to be mathematically consistent, there must be more spatial dimensions than the 3 we observe. Most versions require 10 total dimensions, 9 of space, plus 1 of time. The extra 6 spatial dimensions are thought to be curled up, or compactified, at scales far smaller than any experiment can probe directly. The shape and size of these hidden dimensions determine the properties of particles and forces in our visible universe. Different compactifications lead to different effective physics, giving rise to an enormous landscape of possible universes. Critics argue this makes predictions difficult, as string theory can seemingly accommodate almost any observation. Supporters counter that the landscape may connect to the multiverse and anthropic selection. The hidden dimensions remain one of string theory's most exotic and debated features. Loop quantum gravity suggests space-time itself is made of tiny loops. Loop quantum gravity takes a different approach from string theory. Instead of adding new ingredients like strings, it directly quantizes the geometry of space-time. This bottom-up approach respects the lessons of general relativity while incorporating quantum principles from the ground up. The result is a picture in which space is not continuous but built from discrete, interlocking loop-like structures called spin networks. As these networks evolve through time, they trace out spin foams, a kind of quantum history of space-time. The smallest possible areas and volumes are finite, set by the Planck scale. This granularity removes the singularities predicted by classical general relativity, preventing infinite densities. Loop quantum gravity has been applied to cosmology, offering models where the Big Bang is replaced by a big bounce from a prior contracting universe. The approach is less developed than string theory in some respects, but it provides a compelling alternative vision of quantum spacetime. In this view, space is not continuous, but granular at smallest scales. Classically, space is assumed to be infinitely divisible. Between any 2 points, another point always exists. Loop quantum gravity challenges this assumption. Its calculations show that areas and volumes come in discrete quanta, much like energy levels in an atom. The smallest possible area is of order the Planck area, roughly 10 to the minus 70 square meters. The smallest volume is correspondingly tiny. Such discreteness would have no effect at everyday scales, where countless quanta average into smooth geometry. But at the Planck scale, the granularity becomes fundamental. If space is truly granular, some exotic effects might be detectable in high-energy cosmic rays or gamma-ray bursts traveling vast distances. The search for such signatures is ongoing, though no conclusive evidence has yet emerged. The Planck length is the smallest meaningful unit of distance. The Planck length, about 10 to the minus 35 meters, arises when quantum mechanics, gravity, and the speed of light are combined into a single scale. It is far smaller than any subatomic particle, and trillions of times smaller than a proton. To appreciate this scale, imagine shrinking a human down to the size of an atom, then shrinking that atom down again by a similarly enormous factor. At this scale, the concepts of distance and time as we know them may break down entirely. Quantum fluctuations of spacetime become comparable to the distances being measured, rendering ordinary geometry meaningless. The Planck length sets the arena where a theory of quantum gravity is essential. No experiment has probed anywhere close to this scale. The highest energy particle collisions explore distances billions of times larger. Indirectly, cosmological observations may carry imprints of Planck-scale physics from the very early universe, offering hope for eventual tests. Below that scale, spacetime loses its classical meaning entirely. At distances smaller than the Planck length, the smooth fabric of spacetime predicted by general relativity is expected to dissolve into quantum foam or some other exotic structure. Virtual black holes might pop in and out of existence, and geometry itself would fluctuate wildly. Concepts like up, down, left, right, before, and after may become ill-defined in such a turbulent medium. Classical geometry might emerge only as an approximation valid at larger scales, much as the smooth surface of water emerges from the chaotic jostling of molecules. Different theories propose different pictures of what replaces spacetime: spin networks, strings, causal sets, or something yet unimagined. Without experimental access to these scales, physicists rely on mathematical consistency and theoretical insights to guide speculation. The transition from familiar space to its quantum substrate remains one of the deepest mysteries awaiting resolution, a puzzle that touches the very foundations of reality. Testing quantum gravity directly is beyond any current technology. The Planck scale is so far removed from accessible energies that no foreseeable accelerator can probe it directly. To reach Planck energies, a collider would need to be vastly larger than any machine humanity could build. Even cosmic rays, the most energetic natural particles, fall many orders of magnitude short. This observational barrier frustrates efforts to distinguish between competing theories of quantum gravity. Researchers therefore seek indirect signals, subtle corrections to classical predictions, imprints in the cosmic microwave background, or anomalies in high-energy astrophysics. So far, no smoking gun has appeared. The challenge makes quantum gravity unique among physical theories. Its central regime lies beyond experimental reach. Progress relies on theoretical consistency, mathematical beauty, and hope that nature leaves accessible clues. Physicists search for indirect clues in cosmic rays and ancient light. Although the Planck scale is inaccessible to direct experiment, traces of quantum gravity might be preserved in the universe's oldest messengers. The cosmic microwave background, light released when the universe was just a few 100,000 years old, may carry subtle imprints of quantum fluctuations at the earliest times. High-energy gamma rays traveling across billions of light-years could accumulate tiny delays if spacetime granularity affects photon propagation. Ultra-high-energy cosmic rays, protons accelerated beyond known mechanisms, offer another window into extreme physics. Observations so far have found no definitive signature of quantum gravity. Yet each new generation of telescopes and detectors tightens the constraints, gradually limiting the possibilities and guiding theoretical work. The search continues, driven by the hope that nature left accessible evidence of its deepest structure. Matter and antimatter should have been created in equal amounts. According to the standard model of particle physics, the Big Bang should have produced matter and antimatter in perfect balance. Quarks and antiquarks, electrons and positrons emerged in matching numbers from the hot dense plasma of the early universe. Every particle has an antiparticle, with the same mass but opposite charge and quantum numbers. When particle meets antiparticle, they annihilate into pure energy. If the balance were exact, mutual annihilation would leave only photons behind. Yet our universe is filled with matter, galaxies, stars, planets, and people. The puzzling dominance of matter over antimatter is one of the greatest mysteries in cosmology. Explaining how this asymmetry arose demands new physics beyond our current understanding. The answer lies hidden somewhere in the first microseconds after the Big Bang. If symmetry were perfect, they would have annihilated completely. In a universe with exactly equal matter and antimatter, every particle would eventually encounter its antiparticle. Given enough time in the hot, dense early conditions, annihilation would have been complete. The resulting annihilation turns both into high-energy photons, draining matter and antimatter alike. Within a fraction of a second after the Big Bang, this mutual destruction would eliminate all particles. What would remain is a cosmic sea of radiation with no protons, neutrons, or electrons to form atoms. No stars, no planets, no life. The universe we observe refutes this scenario. Matter clearly surrounds us. Therefore, perfect symmetry did not hold. Somewhere in the physics of the early universe, a bias appeared that allowed a small surplus of matter to escape annihilation. Identifying that symmetry-breaking mechanism is a primary goal of modern particle physics and cosmology. The universe would contain only radiation with no atoms or stars. Had annihilation been complete, the aftermath would be a cosmos of pure energy, photons and perhaps some neutrinos, with essentially no baryonic matter. There would be no hydrogen to fuse into helium, no elements to form molecules, no chemistry, no complexity. The universe would be utterly barren, an endless sea of light with no shores. The elegant structures we see, from galaxies to living cells, depend on atoms persisting long after the Big Bang. Without matter's tiny surplus, the universe would be a featureless expanse of cooling radiation. This thought experiment underscores how finely balanced our existence is on a subtle asymmetry. Understanding why matter dominated is not just an academic exercise, it is the explanation for why anything tangible exists at all. The mystery of matter, antimatter, and their imbalance lies at the heart of our cosmic origins. Something broke the symmetry, leaving a tiny excess of matter. At some point in the first moments after the Big Bang, processes occurred that favored matter over antimatter by a minuscule amount. For roughly every billion antiquarks that formed, there were 1,000,000,001 quarks. After annihilation swept away the matched pairs, that 1 in a billion residue remained. This is all the matter that now fills the universe. Every galaxy, every star, every grain of sand. The mechanism that created this imbalance remains unknown. Physicist Andrei Sakharov outlined 3 conditions that any explanation must satisfy: baryon number violation, violation of charge and charge parity symmetry, and departure from thermal equilibrium. The Standard Model contains hints of these conditions, but not strongly enough to account for the observed asymmetry. New physics is required. For every billion antimatter particles, 1 extra matter particle survived. The ratio of matter to antimatter asymmetry is astonishingly small, roughly 1 part in a billion. In the hot soup of the early universe, nearly every quark found an antiquark and annihilated. Only the infinitesimal surplus remained once the fireworks ended. That tiny leftover produced all the protons and neutrons that make up the atoms we see today. The precision of this ratio has been measured through observations of the cosmic microwave background and the abundances of light elements. Both methods agree remarkably well, confirming this curious imbalance. It is one of the fundamental numbers that define our universe. Explaining why this ratio is what it is, no greater and no smaller, demands an understanding of physics beyond the Standard Model. The surplus may seem negligible, but it is the foundation of a matter-rich cosmos. That tiny surplus became everything we see in the cosmos today. The residue left after annihilation, just 1 quark in a billion, evolved into every structure in the observable universe. Those surviving quarks combined to form protons and neutrons, which later joined with electrons to create atoms. Atoms gathered into gas clouds, which collapsed into stars and galaxies. Stars forged heavier elements and scattered them through supernova explosions. Planets formed from stellar debris, and on at least one such world, life emerged. Every atom in your body traces its lineage back to that early surplus. The entire rich tapestry of the cosmos, from spiral galaxies to human consciousness, owes its existence to a minuscule imbalance in the first fraction of a second after the Big Bang. It is a humbling realization, linking our everyday world to the deepest mysteries of physics. The origin of this imbalance is called baryogenesis. Baryogenesis refers to the theoretical mechanisms by which the observed excess of baryonic matter over antimatter arose in the early universe. Several scenarios have been proposed, each requiring physics beyond the Standard Model. Electroweak baryogenesis envisions the asymmetry forming during the electroweak phase transition, when the Higgs field acquired its mass-giving influence. Leptogenesis proposes that the asymmetry first appeared in the lepton sector, involving heavy neutrinos, then converted into a baryon asymmetry through quantum processes. Afflectine mechanisms invoke scalar fields carrying baryon number that decay asymmetrically. None of these scenarios has been confirmed experimentally. Distinguishing between them may require discoveries at particle accelerators or in cosmological observations. Baryogenesis remains an active frontier where particle physics, cosmology, and astrophysics converge. CP violation shows matter and antimatter behave slightly differently. CP symmetry combines charge conjugation, which swaps particles and antiparticles, with parity, which reflects spatial coordinates. If CP were an exact symmetry, matter and antimatter would behave identically in all processes. Experiments in the 1960s discovered that certain decays of neutral kaons violate CP, and later work found similar effects in B mesons. This CP violation means that processes involving particles and antiparticles can proceed at slightly different rates. Sakharov identified CP violation as one of the essential conditions for generating a matter-antimatter asymmetry. The Standard Model incorporates CP violation through a complex phase in the quark mixing matrix, known as the CKM matrix. Understanding why CP is violated and whether there are additional sources of violation remains a key question in particle physics. The observed CP violation is too small to explain the cosmic asymmetry. While CP violation has been measured in kaon and B meson decays, the magnitude is insufficient to account for the baryon asymmetry seen in the universe. Calculations based on Standard Model CP violation predict an asymmetry many orders of magnitude smaller than the observed 1 in a billion. This shortfall strongly suggests the existence of new physics beyond the Standard Model. Perhaps there are additional sources of CP violation in the neutrino sector, or in yet undiscovered heavy particles. Extensions to the Standard Model, such as supersymmetry or extra Higgs fields, often include additional CP violating phases. Experiments continue to probe rare decays and oscillations, searching for enhanced CP effects. Closing the gap between prediction and observation is one of the motivations driving high-energy physics research today. Unknown physics beyond the Standard Model must be responsible. The Standard Model of particle physics, despite its triumphs, cannot explain the observed matter-antimatter asymmetry. Its mechanisms for CP violation and baryon number violation are too weak to produce the surplus we observe by many orders of magnitude. This failure implies that there must be particles or interactions not yet discovered that played a role in the early universe during the first fractions of a second. Extensions such as supersymmetry, grand unified theories, and theories with extra dimensions all propose new sources of asymmetry. Some predict heavy particles that decayed preferentially into matter over antimatter at high temperatures. Others invoke subtle quantum effects involving neutrinos or new scalar fields. The search for this beyond Standard Model physics is a central goal of collider experiments, neutrino observatories, and precision measurements worldwide. The answer to why matter exists lies somewhere in physics we have yet to uncover, waiting perhaps at energies beyond current accelerators. Some theories propose heavy neutrinos created the original imbalance. Leptogenesis is a leading candidate for explaining the matter-antimatter asymmetry through the neutrino sector. In this scenario, extremely heavy right-handed neutrinos, far too massive to be produced in today's accelerators, existed in the early universe at temperatures exceeding 1 trillion degrees. Their decays violated CP symmetry, producing a slight excess of leptons over antileptons in the primordial plasma. through a quantum process called Sphaleron transitions, which were active in the hot early universe. This lepton asymmetry was partially converted into a baryon asymmetry. The resulting surplus of matter is consistent with observational requirements if the parameters are chosen appropriately. Testing leptogenesis directly is challenging because the heavy neutrinos are beyond experimental reach of any foreseeable accelerator. However, indirect clues may come from low-energy neutrino experiments probing CP violation in neutrino oscillations. If discovered, such signals would provide circumstantial support for the leptogenesis mechanism and point toward physics at extraordinarily high energies. Particle accelerators search for clues in rare decays. Modern particle colliders, such as the Large Hadron Collider, are designed to probe physics at the highest energies accessible to experiment. Among their targets are rare decays of heavy quarks and leptons that might reveal new sources of CP violation or baryon number violation. Even a tiny discrepancy from standard model predictions could point toward undiscovered particles or forces. The LHCb experiment specializes in precision measurements of B-meson decays, hunting for discrepancies with standard model predictions. Bell 2 in Japan pursues similar goals with even higher luminosity. Any anomaly could hint at heavy particles or forces that played a role in baryogenesis. So far, the standard model has withstood all tests, but subtle deviations remain possible. Particle accelerators are our primary laboratories for discovering the new physics that may answer questions about matter's origin. Each collision brings us closer to understanding why the universe is made of matter and not radiation alone. Without this ancient asymmetry, none of us would exist. The matter-antimatter imbalance is not a minor cosmological footnote, it is the reason you can read these words. Had the early universe produced precisely equal amounts of matter and antimatter, complete annihilation would have followed. No protons would survive, no hydrogen would form, and there would be nothing to build atoms, molecules, or living cells. The fact that a 1 in a billion surplus occurred is the foundation of all structure in the cosmos. Every galaxy, every star, every planet, and every living creature owes its existence to that primordial asymmetry. The question of why matter won over antimatter is therefore the question of why anything exists rather than nothing. It is among the most profound puzzles facing science, linking the conditions of the first microsecond to our very presence here. Our universe may be just one among countless others. The notion that our universe exists within a much larger multiverse has gained currency among theoretical physicists. Several frameworks, including inflationary cosmology, string theory, and quantum mechanics, suggest mechanisms for generating many distinct universes. If true, the observable universe is merely a finite patch in an incomprehensibly vast landscape of possibilities. Each universe might have different physical constants, different particles, even different dimensions. The idea is tantalizing but deeply controversial. Critics argue that a multiverse is untestable and therefore unscientific. Supporters counter that indirect evidence, such as unexplained fine-tuning of constants, makes the hypothesis worth considering. Whether the multiverse is a genuine physical reality or simply a useful theoretical construct remains an open question at the frontier of cosmology. The idea of a multiverse arises naturally from inflation theory. Cosmic inflation is a period of exponential expansion thought to have occurred in the first fraction of a second after the Big Bang. In some versions of inflation, once started, the process never entirely stops across all of space. Different regions of space end their inflationary phase at different times, each becoming its own bubble universe with its own cosmic history. This eternal inflation leads naturally to a multiverse of bubbles, each potentially with different physical properties determined by how inflation ended there. Our observable universe would then be just one such bubble, born when inflation ended locally roughly 13.8 billion years ago. The eternal inflation scenario is not an ad hoc addition invented to create a multiverse. It emerges from the mathematics of many well-motivated inflationary models. Testing it directly is enormously challenging, because the other bubbles lie beyond our cosmic horizon, forever out of reach. Nonetheless, its natural emergence from established theory lends credence to the multiverse idea. Cosmic inflation solved many puzzles of the early universe. Before inflation was proposed in the early 1980s by physicists including Alan Guth and Andre Linde, the Big Bang model faced several unexplained coincidences. Why is the universe so nearly flat, balanced on a knife edge between eternal expansion and eventual collapse? Why does distant cosmic microwave background radiation have such uniform temperature, despite regions never being in causal contact to exchange heat? Inflation answers both. The rapid expansion stretches any initial curvature to near flatness and enlarges causally connected patches beyond our observable horizon. It also provides a mechanism for seeding the tiny density fluctuations that grew into galaxies through quantum effects stretched to cosmic scales. These predictions match observations with remarkable precision. Inflation has become a cornerstone of modern cosmology, though the exact field responsible, called the inflaton, remains unidentified. The success of inflation in explaining these puzzles gives confidence that our picture of the early universe, despite mysteries remaining, is broadly correct. Inflation stretched space faster than light in a tiny fraction of a second. During the inflationary epoch, the universe expanded exponentially, doubling in size many times over in a period as short as 10 to the minus 36 seconds, a timescale incomprehensibly brief by any everyday standard. This rate of expansion far outpaces light. Regions that were once neighbors moved beyond each other's horizons almost instantaneously, losing all causal contact forever. Patches of space that started in thermal equilibrium were suddenly stretched beyond any possibility of communication. This superluminal stretching does not violate relativity because it is not matter moving through space faster than light, but space itself expanding, like a balloon being inflated at tremendous speed. Inflation diluted any pre-existing particles, magnetic monopoles, or irregularities, leaving the universe nearly uniform and geometrically flat to extraordinary precision. Quantum fluctuations during inflation became the seeds for later structures, stretched to cosmic scales, where they imprinted on the fabric of spacetime. When inflation ended, the energy of the inflaton field converted into a hot plasma of particles, reheating the universe and beginning the standard Big Bang evolution that produced atoms and eventually stars. This tiny fraction of a second reshaped the cosmos on the largest scales we can observe. Eternal inflation suggests new universes are constantly being born. In eternal inflation scenarios, the inflationary expansion never fully stops everywhere. Some regions of space continue their exponential growth, while others exit and form new universes. While some regions exit inflation and become bubble universes like ours, other regions continue expanding at exponential rates. The space between bubbles grows faster than bubbles themselves, ensuring that inflation persists eternally into the future. New bubbles form continuously, each giving rise to its own Big Bang and cosmic evolution. This picture implies an infinite number of universes being born throughout an ever-expanding inflationary background. Each bubble universe is causally isolated from the others, making direct detection impossible. Nevertheless, subtle signatures, perhaps imprints from bubble collisions in the distant past, might leave traces in the cosmic microwave background. The eternal inflation paradigm transforms our universe from unique to typical, one of infinitely many. Each bubble universe may have different physical laws and constants. Within the eternal inflation framework, each bubble universe forms when the inflaton field decays into a local energy minimum. String theory suggests there are an unimaginably large number of such minima, each corresponding to different values of physical constants and even different low-energy physics. In one bubble, electrons might be heavier. In another, electromagnetism might be stronger. Some universes could have different numbers of spatial dimensions, or different forces entirely. Most of these universes would be inhospitable to any form of complexity or life. We find ourselves in a bubble where conditions happen to permit galaxies, chemistry, and biology. The diversity of possible universes raises questions about which features of our laws are fundamental and which are accidental aspects of our particular bubble. The constants of nature in our universe seem finely tuned for life. The fundamental constants, such as the strength of gravity, the masses of particles, and the cosmological constant, fall within narrow ranges that permit complex structures to exist. If gravity was slightly stronger, stars would burn out too quickly, slightly weaker, and they might never form at all. If the cosmological constant were much larger, the universe would have expanded too rapidly for galaxies to coalesce. Such apparent fine-tuning has struck many physicists as remarkable. Small changes to these constants would lead to radically different universes, most of them devoid of any complexity. Some view it as evidence for design, others as a hint of a deeper physical explanation. The multiverse hypothesis offers an alternative. With many universes sampling many constants, ours is simply one where values happen to permit observers. Regardless of interpretation, fine-tuning remains one of the most thought-provoking aspects of modern cosmology. Slight changes would prevent stars, atoms, or complex chemistry. Theoretical studies have explored what happens when physical constants are varied, even modestly. Increase the strong nuclear force by a few percent, and hydrogen becomes unstable, preventing the existence of long-lived stars. Reduce it, and nuclear fusion cannot proceed efficiently. Change the mass of the electron significantly, and chemistry as we know it collapses. Adjust the fine structure constant, and atoms could not form stable configurations. In many alternative universes, complex chemistry would never emerge, ruling out the possibility of life. The sensitivity of our existence to these numerical values underscores how precariously balanced our world is. It is as if we live on a knife edge between radically different realities. Whether this balance is coincidence, necessity, or selection from a vast ensemble remains hotly debated. The fragility of complexity deepens the mystery of why our universe is the way it is. The anthropic principle suggests we exist where conditions allow. The anthropic principle, in its weak form, is almost a truism. We can only observe a universe compatible with our existence, because otherwise we would not be here to observe anything. If the constants of nature did not permit galaxies, stars, and biochemistry, no observers would be present to notice or ponder the question. This tautology gains considerable power when combined with a multiverse containing many different sets of physical laws. The reasoning shifts from asking why our universe has these particular values to observing that only such values lead to observers who can ask the question. If many universes exist with varying constants, it is no surprise that observers find themselves in a habitable one. Selection effects guarantee it. The strong anthropic principle goes further, suggesting that the universe must have properties that allow observers at some point in its history, though this claim is more controversial. Critics argue that anthropic reasoning can be vague and lacks predictive power beyond what selection effects provide. Proponents view it as a legitimate constraint to be included in cosmological calculations. The debate continues, touching on philosophy as much as physics. In a vast multiverse, our universe is simply one that permits observers. If the multiverse is real, and if physical constants vary from one universe to another, then the question of why our constants are fine-tuned dissolves into statistics and selection effects. Among countless universes with different values, only a small fraction will be hospitable to complexity, yet those are the only ones where life and observers can arise to ask questions. We should not be surprised to find ourselves in a habitable bubble, just as we are not surprised to find ourselves on a habitable planet, rather than floating in the vacuum of deep space. This anthropic selection does not explain why the multiverse exists or why the fundamental laws of physics allow such diversity in the first place. It does, however, shift the emphasis from asking why our universe is special to asking why any universe exists at all, a deeper question that may lie beyond current science. The answer may require future insights we cannot yet imagine. String theory predicts a landscape of possible vacuum states. In string theory, the shape and size of the extra dimensions determine the physics we observe at low energies. There are an immense number of ways these dimensions can be compactified, each corresponding to a different vacuum state, with different particle masses and coupling constants. This collection of possibilities is called the string landscape. Some estimates suggest there could be more than 10 to the 500 distinct vacuum states. Each represents a potential universe with its own physics. The vastness of the landscape makes it difficult to predict which vacuum describes our universe. Some physicists see this as a failure of predictive power, others embrace it as consistent with a multiverse. The landscape has shifted discussions about uniqueness, suggesting that string theory describes not one universe but countless possibilities. The number of possible universes may exceed 10 to the 500. The string landscape contains an almost inconceivable number of vacuum states, with estimates often cited as 10 to the 500 or more distinct configurations. To put this in perspective, there are only about 10 to the 80 atoms in the entire observable universe, a number that already staggers imagination. The landscape dwarfs the number of atoms by hundreds of orders of magnitude, a quantity so large that no comparison to ordinary experience can capture it. If each vacuum represents a possible universe with its own set of physical laws, then the multiverse predicted by string theory is staggeringly vast beyond any hope of enumeration. Among this multitude, only a vanishingly small fraction would have the right conditions for complexity and life, yet that fraction still includes countless habitable worlds. The sheer scale of the landscape changes how we think about fine-tuning and uniqueness. Rather than asking why our universe is special, we ask how we come to inhabit a hospitable corner of an almost infinite ensemble of possibilities. The many worlds interpretation of quantum mechanics suggests branching realities. The many worlds interpretation proposed by Hugh Everett in 1957 offers a radical solution to the measurement problem in quantum mechanics. According to this view, every quantum event that can have multiple outcomes does have all of them, each realized in a separate branch of reality. There is no collapse of the wave function. Instead, the universe continually splits into parallel copies. In one branch the particle went left, in another it went right. Observers in each branch see only one outcome, but all outcomes are equally real. This interpretation is deterministic and preserves unitarity, features that appeal to some physicists. No mysterious collapse is required. The wave function simply evolves according to the Schrödinger equation. Others find the proliferation of branches extravagant or untestable. Debate continues, with many worlds remaining one of the most discussed interpretations in foundational physics. Every quantum measurement may split the universe into parallel outcomes. If the many worlds interpretation is correct, then every time a quantum measurement is made, the universe does not pick one result while eliminating others through some mysterious collapse process. Instead, all possible results occur, each in its own branch of reality that continues evolving independently. When an electron's spin is measured, one branch records spin up and another records spin down. Both outcomes are equally real. Each branch contains observers who remember only their own measurement result. The observer in each branch becomes entangled with the outcome they witness, unaware of the other branches and their different histories. This branching happens constantly at every quantum level event across the cosmos, from radioactive decays to photon absorptions. The number of branches would be incomprehensibly vast, growing exponentially with each passing moment as new quantum events continually occur. Whether these branches are true parallel universes in any physical sense, or merely a mathematical convenience for calculations, is a matter of ongoing philosophical debate. The many worlds picture challenges intuitive notions of reality, but is taken seriously by many prominent physicists and philosophers. Other universes would be forever beyond our cosmic horizon. Whether arising from eternal inflation or the quantum many worlds interpretation, other universes would be causally disconnected from ours for all practical purposes. We could never send a signal to them or receive one back, no matter how advanced our technology becomes. They lie beyond the cosmic horizon set by the speed of light and the finite age of the universe. In the eternal inflation picture, other bubble universes recede faster than light as the inflationary background expands between them exponentially. In the many worlds picture, branches decohere and become mutually inaccessible, splitting into separate histories that never again interact. This inaccessibility is what makes the multiverse so controversial from a scientific standpoint. It cannot be directly observed or definitively falsified by any conceivable experiment. Yet some argue that theoretical consistency and mathematical elegance can guide us even where direct observation cannot. The question of whether science can ever confirm or refute the multiverse remains hotly contested among physicists and philosophers alike. Some theorists search for traces of collisions with other bubbles. Although direct observation of other universes is impossible, some physicists have sought indirect evidence. In eternal inflation, bubble universes could occasionally collide, leaving faint imprints on the cosmic microwave background as circular patterns of anomalous temperature. Several studies have searched for such signatures, but results have been inconclusive. The cosmic microwave background is examined at ever higher resolution, looking for telltale, disc-shaped temperature anomalies. Claimed detections have not withstood scrutiny, and no robust evidence for bubble collisions has been found. If such signals were confirmed, they would provide powerful support for the multiverse and for eternal inflation. For now, the search continues, pushing the limits of what cosmological observations can reveal. Even a null result constrains the models, tightening the range of possible inflationary dynamics. The quest demonstrates that even the most exotic hypotheses are not entirely beyond empirical reach. The multiverse challenges what it means for a theory to be testable. Traditionally, scientific theories are valued for their testable predictions. If a prediction fails, the theory is revised or discarded. The multiverse poses a challenge. If other universes are forever beyond observation, how can we test whether they exist? Some argue that indirect evidence, such as fine-tuning or theoretical consistency, can support the multiverse even without direct observation. Others insist that a hypothesis immune to falsification is not science at all. This debate touches on deep questions about the nature of scientific knowledge. Is testability a strict requirement, or can coherence with other well-tested theories suffice? The multiverse has pushed physicists and philosophers to re-examine these foundations. The outcome will shape how future theories are evaluated and accepted. Critics say the multiverse may belong more to philosophy than physics. Skeptical physicists view the multiverse as speculation, unanchored by experiment. Without observational support, the idea risks becoming more philosophy than physics. They warn that accepting untestable ideas risks blurring the boundary between science and metaphysics. Without the discipline of empirical check, they argue, theory can wander far from reality. Proponents counter that the best current theories naturally produce multiverses, making it intellectually dishonest to ignore them. The debate is ongoing, and often spirited. What all sides agree on is that the question matters. How we decide what counts as science influences how we pursue knowledge about the universe. Whether the multiverse ultimately gains acceptance or is relegated to philosophical curiosity depends on future developments in both theory and observation. For now, it remains a fascinating frontier at the edge of science. Yet the mathematics of well-tested theories point toward its existence. Cosmic inflation, supported by observations of the cosmic microwave background, leads naturally to eternal inflation, and thereby to a multiverse of bubble universes. String theory, developed from established quantum field theory principles, predicts a vast landscape of possible vacua. Quantum mechanics, the most precisely tested theory in science, gives rise to the many worlds interpretation when taken at face value. None of these theoretical extensions was invented to create a multiverse. Rather, the multiverse emerged as an almost unavoidable consequence. This emergence from mainstream, well-tested frameworks gives the multiverse a credibility that purely speculative ideas lack. The multiverse is not wishful thinking, but rather a logical consequence of our best current theories. If nature truly follows these mathematical paths, then additional universes may be as real as our own. The challenge is to find ways to confirm or constrain this remarkable possibility. Understanding reality may require accepting its immense diversity. If the multiverse is real, our universe is neither unique nor special. It is one among countless possibilities, selected by the anthropic condition that observers can only exist where conditions permit. This perspective is humbling. Everything we see and know may be a tiny corner of an unimaginably vast ensemble. Yet it is also unifying, placing our existence within a broader cosmic context. We become not isolated accidents, but representatives of the rare conditions that allow complexity to flourish. Rather than diminishing the wonder of our universe, the multiverse deepens it by revealing the scope of what reality might encompass. Accepting such immense diversity challenges our intuitions, but may be necessary for a complete understanding of nature. Science has often expanded our horizons beyond initial comfort, and the multiverse may be the next great expansion. The greatest mysteries remind us how much we have yet to learn. Despite remarkable progress over the past century, fundamental questions remain stubbornly open. What is dark matter made of, and will we ever detect it directly? Why does dark energy exist, and is it truly constant or slowly evolving? How can gravity be reconciled with quantum mechanics into a single unified framework? What happens at the center of a black hole, where our theories break down completely? Why does matter dominate over antimatter, allowing atoms and stars to exist? Is there a multiverse beyond our cosmic horizon, forever hidden from observation? Each question points to genuine gaps in our understanding that await future discoveries. Science thrives on such mysteries, drawing generations of curious minds to probe the unknown. Every answered question reveals new questions behind it, an endless frontier of knowledge stretching as far as imagination can reach. The mysteries we have explored tonight are not failures of science, they are invitations to further inquiry and deeper wonder. Science is not diminished by mystery, but enriched by it. Mystery drives discovery, and every great advance in physics began with questions that seemed unanswerable at the time. Dark matter and dark energy were once unknown phenomena, hiding in plain sight. Now they are central pillars of cosmology. Black holes were once theoretical curiosities, mathematical oddities in Einstein's equations. Now we image their shadows with radio telescopes and hear their mergers in gravitational waves rippling across the cosmos. The unsolved puzzles of today are the breakthroughs of tomorrow, awaiting only the right insight or observation to unlock their secrets. Far from diminishing the achievement of science, mysteries highlight its dynamic, self-correcting nature and its endless capacity for surprise. Each unknown is an opportunity, an open door to deeper understanding and richer knowledge. The universe keeps revealing new layers of wonder, and science is our method for exploring them systematically. As you drift into sleep, let the mysteries accompany you, gentle reminders that the cosmos has more secrets to share, and that curiosity is among the greatest gifts of the human mind. And now the quiet wonders of the universe's deepest mysteries begin to gently fade into the stillness of sleep. You have wandered through over 100 peaceful truths about the unknown places of the cosmos. From invisible matter that holds galaxies together, to invisible energy that pushes them apart. From black holes where time and space twist beyond recognition, to the paradoxes of information that may never truly disappear. You have explored how quantum mechanics and gravity remain at war in the most extreme conditions. You have learned about the delicate imbalance that allowed matter to exist at all. And you have considered the possibility that our universe is merely one island in an infinite archipelago of realities. You are connected to this story more deeply than you may realize. Right now, as you listen, dark matter is shaping the galaxy that holds your planet. Dark energy is gently stretching the space between distant stars. Quantum effects are flickering at the heart of every atom in your body. The same forces that govern the cosmos govern you. If your eyes feel heavy now, let them close. Let the rhythm of your breath become steady, like the slow expansion of space itself, like the patient drift of galaxies moving through the dark. Tonight, as you rest, the mysteries continue their silent unfolding. Dark matter halos embrace distant galaxies. Dark energy stretches the cosmic web ever wider. Black holes swallow light and keep their secrets. And somewhere beyond all horizons, the unknown waits with infinite patience. You are a small, warm presence within this vast, mysterious cosmos, peacefully resting among the wonders. Sleep well, sweet dreams. And may you carry with you the quiet knowledge that the universe, for all its strangeness, has made a place for curious minds like yours to wonder and to rest. Thank you for joining me on this journey through the greatest mysteries of the universe. If you enjoyed this video, please subscribe to Drowsy Discovery for more soothing explorations of the cosmos and the questions that still await answers. There are more wonders waiting, more secrets hidden in the darkness between stars, more gentle truths to drift through on quiet evenings. Rest well, and may the quiet mysteries of the universe keep you company through the night. This has been Drowsy Discovery. Good night.